Hello students, in this video we'll discuss arc length and surface area of revolution for parametric curves. If we're given a parametric curve, x equals f of t, y equals g of t, for t in a range between a and b, what we can do is we say that the arc length parameter, the arc length, of the curve is given by the formula. S is the integral from a to b of the square root of dx dt, dx dt squared, plus dy dt squared dt. That is the arc length formula. We'll see in a future video how to derive this formula, but in this video we're just going to be principally concerned with computing this thing, okay? And so what we can do is this gives you the length of arc, so that's one formula we have. Okay. And the other thing we want to talk about is once we have the arc length, we can compute surface area from this. So the surface area obtained by rotating the curve along the y-axis, or around the x-axis rather, along the x-axis, is the integral from a to b. So this is going to be surface area of the solid that's generated, integral a to b. And I have a 2 pi times whatever y is on this formula. So it's going to be y of t. That's the height. And then times the arc length parameter over here. So typically you write ds, but I'll draw out the full formula over here. It'll be what? It'll be dx dt squared plus dy dt squared dt. That will give me the surface area. Now let's see an example of doing both these things simultaneously. So what I can do is I can consider, for example, a famous curve, the asteroid curve. So it's this asteroid curve. Its x is cosine cubed of t, y is sine cubed of t between 0 and 2 pi, okay? And I'll change the parameterization. I'm going to find the arc length of this thing first. So what's the arc length? The s is going to be the integral from 0 to 2 pi. And we have the square root of what? The square root of 3 cosine squared of t. Then I'm going to put, it's technically it would be negative sign, but since it's being squared, I'm just going to avoid that negative sign for notational convenience. And then what? And then plus, maybe I should put the negative in there just for it to be completely correct. And then what? Then 3 sine squared t, and then a cosine t quantity squared, okay? dt. Now it looks like an ugly mess, but let's see we get total over here. So total over here, everything is a factor of 9, so I'm going to pull that out. That's going to be 3, the integral from 0 to 2 pi, right? And then cosine to the fourth of t sine squared of t plus sine squared to the fourth of t cosine squared of t, and that's all the 1/2 power dt. And so we'll just simplify too, so I can pull out a factor of cosine squared sine squared. So from that square root, I'm able to pull out what? I'm able to pull out integral from 0 to 2 pi. Just a what? Just a factor of sine times cosine. Cosine t sine t absolute value, right? And then what? And then we'll have a factor what's left over. I'll have a cosine squared plus sine squared, so that's just 1 left over. So I have a dt over here, okay? Good. All right, so now the easiest thing to do is to note that if we want to integrate this, we have to do case-by-case basis because I'm going all the way from 0 to pi over 2. But rather than do that, let's note that this thing is symmetric, right, in this region over here. So what I have to do is, all I'm going to have to do is look at the integral over one portion of this, okay? So I can do a couple different things. So let's actually break it up into, as a good practice with integration, let's break this up into 3 terms, right? It's going to be 3, the integral from 0 to pi over 2. Both of them are positive over here, so I'm going to have a cosine t sine t dt. Then when I'm between pi over 2 and pi, then that says the cosine is going to be negative, so and the sine's positive, so I'm going to pull out a negative sign. So then minus the integral from pi over 2 to pi of sine of t cosine of t dt. Between pi and pi over 3, they're both negative, so I don't need anything. So I have an integral from pi to 3 pi over 2 of sine t cosine t dt. And finally what? And finally the last integral over here is going to be the integral from 3 pi over 2 to 2 pi. And now one of them is negative. Now the sign's negative, so I need a negative sign over here. So this is going to be a negative sign. So that sign over there is negative. Negative. And then cosine of t, sine of t, dt. Okay? Now, of course, this is really what? Each of these terms over here is really half, 1/2 the sine of 2t. So an antiderivative of these things is going to be what? It's going to be negative 1/4 cosine of 2t. So we're going to have 3, and then over here it's going to be a negative 1/4 cosine of 2t from 0 to pi over 2. And then what? And then we're going to have a plus 1/4 cosine of 2t from pi over 2 to pi. And then a minus 1/4 cosine 2t from, that's a quarter of course, from pi to 3 pi over 2. And then finally a what? A plus 1/4 cosine 2t from 3 pi over 2 to 2 pi. Okay? Let's see what we get over here. So I'm going to have the cosine of pi, that's going to be give me a 1/4. Then I'm going to have a what? Then minus the cosine of 0, that's going to give me a what? A total factor of what? Let's think for a second here. So when I plug in pi over 2, that's the cosine of pi, which is negative 1. So that's a positive 1/4 minus a quarter. So these terms are going to give me a 1/2 over here. Let's see what these terms over here give me. When I plug in pi over here, I mean the cosine of 2 pi, which is 1. When I plug in negative 1, that's the cosine of, when I plug in pi over 2 with a negative sign, that's the cosine of pi, which is negative 1. So that also gives me a 1/2. That's another 1/2. Over here, what's going to happen? I'm going to have the top limit is going to be the cosine of what? The cosine of 3 pi, which is negative, so I get a positive 1/4, and then minus, that's also a 1/2, and by symmetry, this thing over here is also going to be half. So we can see I could have either symmetrized this from the outset, but it's good to actually go through the integration practice to make sure this makes sense to you with doing absolute value integrals. Okay, so I have a half, that gives me a factor of 2, so I have 3 times 2, and that gives me a 6. So the arc length of this asteroid is equal to 6 around 1 full cycle of it. Thank you very much.